Good, how are you? Good to see you too, yes. The official satellite software of the 33rd Space Symposium is produced by Analytical Graphics. This year, they have sponsored the complimentary Wi-Fi we are all enjoying. As our next panel comes to the stage, please enjoy this brief video from AGI. Good morning. My name is Major Eleanor Morgan, and I will be serving as your new Gen Master Moderator for today. A quick little background about me. I'm a 2006 Air Force Academy graduate, a former C-17 aircraft commander, and now I am an instructor pilot and evaluator for remotely piloted aircraft for the Air Force. I currently serve as an electronic combat officer and a mission director at our Wing Operations Center, and there I oversee the 24/7 combat operations for our global MQ-1 and MQ-9 aircraft. I've been involved with the Space Generation Advisory Council for the last 3 years, and yes, I give a plug. And I'm also on the organizing committee for the Space Generation Congress in Adelaide, Australia this fall. And without further ado, our first panel this morning will give us a look at the future as it addresses heavy lift, creating opportunity for deep space exploration. To lead our discussion, please welcome the Executive Director of the Coalition for Deep Space Exploration, Dr. Mary Lynn Dittmar.
Good morning. So thank you all for being here. We're going to do a panel today that's a little different than normal. When talking about heavy lift, very often we have lots of technical discussions about the nature of the vehicles themselves. Or there tends to be a focus of late with regard to heavy lift in terms of how it enables human space exploration. Today we're going to touch a little bit on those things, but we're going to focus on the capability itself and what it provides for us going forward with regard to exploration, science, emphasis on the science, as well as development of the solar system. So I'm going to do just a little brief sort of ad here for the coalition so you know who I am and why I'm here. I need to get my slides flipped. Taking my thing back from John already. Okay, so about the coalition. We're an industry trade association, 70 companies and growing. The mission is to ensure the United States remains at the forefront of human exploration, science, technology, and economic development of space by reinforcing the value and benefits of deep space exploration and science with the public and our nation's leaders. Our focus platform-wise is the International Space Station, SLS Orion Exploration Ground Systems, then the James Webb Space Telescope, Juno, OSIRIS-REx, WFIRST, Europa, pretty much all of NASA's flagship science missions. That's just a little brief thing about where you can find us. And again, sort of to move on here about heavy lift. It's a vital tool in the toolkit of exploration and science. It's a critical capability for sustained human exploration of deep space, but it's equally critical for science. And so what we want to do is spend a little time today exploring that and the capability itself and what it enables across the board. So I'm going to begin by introducing very briefly, I'm going to skip bios because we've only got about 45 minutes for this entire panel. I'm just going to introduce very briefly our speakers, and then I'm going to hand it over to the one on my right. So I'll begin with John Grunsfeld. Dr. John Grunsfeld is the former Associate Administrator for NASA for the Science Mission Directorate, former NASA astronaut, and I'll say former Hubble repairman par excellence. To his right is Dr. John Ehrenberg. John is the Chief Engineer for the James Webb Space Telescope. To my immediate left is Rob Meyerson. Rob is the President of Blue Origin. Since 2003, he has guided the steady growth both of the company and its capabilities. And to his left is Mike Woods. Mike is the Chief Engineer for Boeing's Space Launch System. So I'm going to begin by handing it off to you, John.
Thank you very much, Mary Lynn. And if we could bring up my slide pack, please. For various parts of this conference, especially when we have our uniformed officers in the room, and I see a few in the audience, we talk about space dominance, we talk about shock and awe, rapid dominance as a military doctrine. Today we want to talk about wonder and awe. And the United States is truly the world leader in space and earth science. We have an incredible program. We are trying to answer fundamental questions about the universe. And if we bring up the slides, we're trying to answer questions such as where did we come from? Where did the universe come from? How did our solar system develop? Where do the chemical elements that we're made out of form? The answer is inside of stars and ejected in supernova. Where are we going? What's the trajectory of planet Earth? What's the trajectory of the universe? What's the trajectory of the climate of planet Earth? Controversial question these days. And a big question is, are we alone in the universe? Is there life elsewhere? And the amazing thing is, all of these today are questions which are well-posed scientific questions for which we have the technology and the capability to answer. And that's what's really so exciting. Of course, the obvious case is Mars. And the obvious case for heavy lift is Mars. NASA's done studies, for decades, and each time the answer is heavy lift is transformative. And from a science perspective, humans on the surface of Mars, I believe, will be transformative. We've been able to get, the 2,000-pound, 1 metric ton Curiosity on the surface. Curiosity has a Twitter account. Curiosity has been discovering amazing things on Mars, sort of, except the rover hasn't discovered anything. People back on Earth have. And even though it's the best we can do today, it's extraordinarily limited. The pace of discovery is painfully slow. I think when we have scientists and engineers on the surface of Mars, we'll be able to make much more rapid progress. And that's an obvious case where heavy lift is enabling. But there's others. In the search for life in the universe, there's a possibility that there could be life under the ice of a moon of Jupiter, Europa. It has a salty, warm ocean. It's been that way for 4 billion years. And in fact, heavy lift will allow us to send the Europa Clipper to Europa. And it's transformative, and you'll hear about this. Instead of a 7-year trip that involves a Venus, Earth flyby, and then a long cruise out to Jupiter and to Europa, a heavy lift vehicle like SLS could get us there in under 3 years. Now, that's important because inquiring minds want to know. It shortens the time. But all of you in the space industry know that time is really money. If you have a team of hundreds of scientists and engineers waiting 5 or 6 years, at $50 million a year, that's real money waiting to get to the destination where it starts to get interesting. But of course, we found out from the Kepler satellite the universe is filled with planets. Our solar system is teeming with solar systems. And the Kepler satellite and others have been discovering this. We're finding solar systems that have an architecture like our own with rocky planets in the habitable zone. We want to find out, is there life there? What's that going to take? Well, we're on track for an October 2018 launch of the James Webb Space Telescope, the most amazing telescope we've ever built, 20 feet across, 6.5 meters, segmented optics that operates at 40 Kelvin, an incredible machine. But it's not big enough to find out if we're alone in the universe. But we know how to build things, and we know how to build something that could give us the data we need to start seeing the blue sky of one of those exoplanets, if it has a blue sky, if it has an atmosphere. If it has water, we should see signs of water in the atmosphere. If it has oxygen, which is one of these biomarkers, plants produce oxygen in our atmosphere. Absent plants, we'd have a CO2 atmosphere and a nitrogen atmosphere. Methane, carbon dioxide, all of these indicators, but it's going to take a big telescope to do that. And I believe we're going to have to build that telescope because it has to be big. And Earth 2.0 is going to be incredibly faint. To give you a reference, fainter than the faintest galaxy in the Hubble Deep Field. We know how to build things. We serviced Hubble, built the International Space Station. So I think heavy lift would enable us to build a telescope that could tell us whether we're alone in the universe. This is just a cartoon of an Orion and an assembly vehicle assembling a 20-meter telescope. That would do it. We have the technology to do this today. For the first time in human history, we also have the means to launch these. The Space Launch System is one example that can launch Orion, could launch a Europa mission, a large telescope, a mission to Mars. But the family is growing rapidly. There are new entrants. On the left, you can see missions that are flying now: Soyuz, Antares, Ariane 5, Atlas 5. But you go to the right, and we have new vehicles, including, as you'll hear, Blue Origin with New Glenn and the Space Launch System. This is the best we can do today. That's the James Webb Space Telescope, 20 feet across. We fold it up and we put it in a fairing, and that's small compared to what new capability is coming online. Imagine what we could do putting the pieces of a telescope into a fairing and having astronauts go up and assemble it, or robots. Really transformative, both for space science, for astronomy and astrophysics. And of course, telescopes can look down too, and that's all I'm going to say about that. But we need to be bold. We needed to be bold to do Hubble. We're audacious with the James Webb Space Telescope, but we know how to build bigger, and we know how to answer these fundamental questions. So with that, I'll just leave you with the wonder and awe. Imagine the moment when a telescope says, we know there's another Earth out there, Earth 2.0, and we see signs of life. And with that, I'll hand it over to John.
Thank you, John.
Thank you very much, John. I'm going to follow up here and talk about large boosters as an essential element in continuing the advances and the excitement that John so eloquently outlined. So let's start off with a few points. If you can go back a slide, it's a hair trigger here. In terms of what makes a scientific mission compelling, what makes it worth that large investment, it has to be a significant improvement in sensitivity over what's gone before, and we'll see the evolving trend here in a moment. The science can't be achievable from the ground, so it has to be uniquely done from space. Detection of life on other planets, X-rays, far infrared are examples of these exciting fields. And finally, we have to be able to execute it in a reasonable time and within the cost and funding available. Only a large telescope, as we discovered earlier today, can help us identify whether life is prevalent or habitability is prevalent in the universe. You see here a series of images. These are known stars that are accessible with 4, 8, and 12-meter telescopes. With the expected population of Earth-like planets, with a 4-meter telescope, we can only detect 4 Earth-like planets. As we get to larger and larger telescopes, that becomes a scientifically significant and important and compelling argument. And so to get to samples large enough to determine if life is common on these common Earth-like planets, we need a large telescope to collect the light, to analyze it, to make a meaningful scientific conclusion. We see here the largest telescopes in space for both visible and infrared. You can see the Hubble Space Telescope, the James Webb Space Telescope, and the yellow dot with the error bar. I am an engineer after all, can't do a graph without an error bar, are the potential ranges of the future telescopes that John alluded to earlier, anywhere from 8 to 15 meters. This is wonderful. We're on the trend. There's a tiny problem with this. I call it the tyranny of the fairing. So Webb has been designed to fit into the existing 5-meter fairing. This requires a large number of deployments and releases. It's elegant, exquisite engineering. We're working very hard to make all of this work exactly as we've planned. But studies show that we're limited to 9 meters on the best day of fitting into an existing fairing. This limits us. If you put that frontier on the same trend, you find that most of the scientific promised land is beyond the frontier. It's not accessible with current boosters. Which brings me to my conclusion that scientific advancement, the kind of wonder and awe, the inspiration that we want to give ourselves and the next generation requires these larger boosters. It gives us greater mass and volume to space. It's an efficient means of getting even larger systems into space, the possibility of in-space and assembly and test, and it's foundational to the continued progress in space astronomy. Thank you.
Okay, thank you, Mary Lynn, and thank you everyone for being here. This is the heavy lift panel, but if you came today to learn how we lifted a heavy rocket out in front of the summit circle, sorry to disappoint you. So, our vision at Blue Origin is a future with, where millions of people are living and working in space. And this started as a dream of our founder, Jeff Bezos, when he watched Neil Armstrong walk on the moon. And he realized that dream when he founded Blue Origin. This is a very, very long-term effort we're talking about, and we often think in terms of decades. Our motto is Gradatum Ferociter, which is step-by-step ferociously, and that explains our approach. The desire to explore is a fundamental part of who we are as human beings, and it's also very important for our survival. And that's why we are so driven at Blue Origin to build rockets and systems that allow for reliable, cost-efficient access to space, including deep space. New Shepard, our suborbital system is New Shepard, named after Alan Shepard, the first American in space. We're using New Shepard to teach ourselves how to launch, land, and efficiently launch rockets again and again. Because we can launch and land New Shepard for several orders of magnitude lower than the cost of an orbital launch, we will gain a lot of experience at a low cost. Over less than a year, we flew the same New Shepard rocket to space and back 5 times, demonstrating not only reusability, but multiple reuse of the same booster. Now, perhaps some of you have seen it outside, and if not, I do hope you get a chance to go check it out. On our last mission, we conducted a really cool test of our capsule escape system, and I want to show you that, so let's take a look.
Good morning, everyone, and welcome to the live stream of today's Blue Origin test flight.
So everything seems nominal for an exhilarating test flight.
Today's mission is totally focused on a successful crew capsule escape with the understanding that the booster will likely be lost. It's time to hand this show over to Mission Control so we can listen in on the final countdown.
I'm super excited to see this thing go.
Godspeed, New Shepard.
5, 4, command start, 2, 1. Cleared the tower.
There you have it, a spectacular launch of New Shepard, live from West Texas.
Coming up here around 45 seconds is when we'll see our escape.
There it is, 70,000 pounds of thrust pushing that crew capsule.
And the B-3 engine remains on, the booster continues to space.
The drogues are out on the crew capsule. There go the mains.
Okay, so those 3 mains are reefed right now to keep them small. The reefing will remove shortly to fully expand, as you can see.
And touchdown of the New Shepard crew capsule. From what we can tell, that was a nominal in-flight test of our escape system. And again, all astronauts on board would have had a pretty exhilarating ride, but a safe ride.
The B-3 will restart, and we'll wait for that smooth, gentle descent onto the pad. There she goes. Look at that. Nice and stable. Landing gear deploying. There you go. The booster's leaving. That tail fire's got set and shut. Beautiful.
Wow. There it is.
Touchdown!
What an extraordinary test and a tremendous final flight for both craft. If you're interested in learning more and keeping up to date on our progress, be sure and sign up on our website for email updates. And until our next exciting launch, Gradatum Ferociter.
Okay. The design and operational lessons learned from New Shepard are already being directly applied to New Glenn, our orbital rocket. Our New Glenn orbital system is named after John Glenn, the first American to orbit the Earth. New Glenn is rather large by comparison to other current rockets, but it is the smallest orbital vehicle we will ever build. It's designed to take satellites, people, and just about anything into space, far into space. And it comes in two versions, the two-stage variant, as is shown here on this graphic, and a three-stage variant. Target performance for the two-stage variant is 13 metric tons to GTO and 45 metric tons to low Earth orbit. And the reusable first stage has some aerodynamic characteristics. The strakes on the lower section of the booster allow it to fly back for landings and saving fuel needed to propel payloads into space. And those strakes also allow us to minimize the deceleration burn during entry, which is a big payoff in terms of performance. Now let's take a quick look at New Glenn. New Glenn's main stage is powered by 7 BE-4 liquid oxygen liquefied natural gas engines, which together will generate over 3.85 million pounds of thrust. That BE-4 engine, we just announced a couple of weeks ago that we had shipped it from our Kent facility to our West Texas site. And here it is. We're going to begin testing very soon on our test stand down in West Texas. I'm very proud of our team for designing and building the world's largest LOX LNG engine. It's designed for 100 flights, and we expect New Glenn to fly in 2020, and I'm excited about all the payloads that we're going to be able to launch. Reusability is the holy grail of rocketry. With New Shepard, we've demonstrated rapid reuse of a space vehicle, but we're still in the very, very early stages, and we're continuing to drive towards operational reuse. We want to drive to a future where reuse is the norm, and our commercial customers have already embraced reusability. They are focused on price, reliability, and schedule, and reusability will enhance all three of those. Last month, we announced our first agreements with Eutelsat and OneWeb for 6 launches, so we are making progress towards that goal. Now let's talk about exploration. If NASA undertakes crewed lunar exploration, more cislunar logistics capacity will be required. We believe that commercial systems and services can augment NASA systems to meet the logistics and resupply needs of longer crewed missions in lunar orbit and enhance NASA capabilities. Blue Origin has recently proposed a lunar lander architecture to cost-effectively soft land large amounts of mass onto the lunar surface. Any credible first lunar settlement is going to require such a capability. We believe that the lunar surface offers valuable resources with valuable science return that can serve as a location to demonstrate key technologies and serve as an appropriate location for that long-term permanent settlement. We also believe the moon is in sequence for longer-term exploration of the solar system, including Mars. Blue Moon is Blue Origin's in-space transfer and lunar lander architecture, leveraging Blue and NASA technologies. Blue Moon directly leverages our New Shepard proven vertical takeoff and vertical landing technology combined with our extensive liquid propulsion capabilities to reduce development time and risk. Blue Moon is designed and optimized to fly on NASA's Space Launch System, but can also fly on a number of different launch vehicles, including the Atlas V and New Glenn. And we're willing to invest in its development as part of a public-private partnership with NASA. The more NASA flies SLS, the more they will need commercial logistics delivery services. New Glenn and Blue Origin and Blue Moon complement SLS and Orion, enabling NASA's return to the moon, and this time to stay. These are the first steps we're working on to enable our vision of millions of people living and working in space. Thank you.
Thank you, Rob. Mike?
Rob, congratulations to Blue Origin on your success and many continued success. I think all of our capabilities are complementary. It's a and proposition, not an or, and we look forward to your continued success. And it warms my heart to hear Jonathan and John talk about the science and how SLS can enable that. And I can say on behalf of the SLS team, NASA and industry, we look forward to eliminating the tyranny of the fairing and having you feel volume constrained and to some extent even mass unconstrained, I should say. So I'll be brief to allow a little time for question and answer. Just a quick update on where we are on the SLS. We have built most of the primary structure. We're wrapping up that year. We finished the structural qual article for the engine section. It's getting ready to be barged to Marshall fairly soon for qual testing. The upper stage, the interim cryogenic propulsion stage for the first EM1 flight in 2018, the flight article has been completed, shipped to the Delta Operations Center at the Cape, and it's ready, standing by for flight. We are rapidly finishing up our heavy qualification activities on our avionics, about 3/4 of the way through our subsystem qualification. The majority of the parts, millions and millions of parts, tens of thousands of part numbers are on the dock at MAF and going through the assembly process for the core stage. And so we're looking forward to wrapping that up shortly. You can see on the right side of the chart the liquid hydrogen tank, 130 foot tall, and the friction stir well, the self-reacting friction stir well at the Michoud assembly facility, largest friction stir welder in the world. That's 130 foot tall. Again, we're finishing up that and getting into the assembly operations to finish up all the qual articles and flight articles. The engine section shown on the left there. As I mentioned, getting ready, finishing up the instrumentation checkout for its qualification testing at Marshall. And with that, I'll be brief and turn it over for some Q&As.
Thanks, Mike. Okay, what we're going to do is a little bit of discussion up here with the panelists, and then I think that the Space Symposium has made available the capability to text in some questions, which I have kind of coming up here on an iPad in front of me. So I don't actually know what the mechanism is to do that, but hopefully you all do. Let me start talking a little bit about Mars, sort of pick up on John's initial graphic, sort of showing us heading that direction. How do human exploration and science work synergistically, enabled by heavy lift, to help us carry out missions of discovery there at Mars?
Well, first of all, there's a graphic on some of the screens if you look in the back of the room, although it looks a lot like West Texas as well. If you saw those amazing Blue Origin imagery in the film. But to get to Mars today with the largest rockets that we have, as I mentioned, we're able to get 1 metric ton on the surface. And there's lots of astronauts who would sign up to go in essentially a go-kart today. Your longevity would probably be pretty short. We really need to be able to get 5 or 10 metric ton pieces to assemble the ability to have humans on the surface of Mars. And that's going to require I think, assembly in space, but also heavy lift to launch from the Earth. But it comes back to the question of, why are we going to Mars? And there's all kinds of reasons for exploration, but for going to Mars. But I think the early crews are going to be scientists, planetary scientists, astrobiologists going to Mars to answer these fundamental questions. And by getting human-scale systems where the future astronauts can live, you also have the capability to bring amazing analytical instrumentation, mass spectrometers, scanning electron microscopes, the kind of tools we have on Earth that are just too big to put in a robotic probe and that require delicate manipulations of nano-size samples to look for organics that might be due to either existing life on Mars or ancient life on Mars, if we're going to answer this question. Now, Mars is not just a planet that 3 billion years ago was much like Earth, could have harbored life. It's also unique in our solar system in that it's the only planet in our solar system that we eventually can really live on. The moon is a nice place to visit. You can build habitats, but it doesn't have the resources in the environment that is Earth-like enough for humans unless we evolve to be lunatics. Thank you. That Mars we can really live on. And so, that offers opportunities in terms of in situ resource utilization and engineering challenges that, again, it's going to require heavy lift to get that kind of industrial machinery to the surface of Mars. Now, there's opportunities perhaps to make some of that, using, additive manufacturing and other things, but that's a little ways off. So I think the early missions really require heavy lift to be able to get the pieces that we know will work to the surface of Mars.
Thank you. Jonathan, if you had your brothers and you were going to build the fantasy telescope, I'm sure you've thought about it.
Mm-hmm.
What would be your next step? What would you like to see happen? And how would heavy lift help you with that?
Heavy lift would make it possible. We all want to get to that scientific position of that 60 or 100 Earth sample, being able to image every galaxy in the universe and see the star-forming region, understand how supermassive black holes play a role in the universe. And that really demands a much larger telescope, so the 25, 30 meters. Whether it gets assembled on the ground and unfolds or it gets assembled in space, detailed studies will tell us. But it would be worth, how amazing would it be to take that bold leap and to take the challenge and say, yes, we can do this in 10 years. And so heavy lift enables us to do that. If we have to do it in pieces, if we have to do it in multiple launches, we just can't take that daring leap. And so my dream would be to build the astronomers that dream telescope to really open up questions. Heavy lift just makes that possible. It's not possible without it.
I love the expression, the tyranny of the fairing. I'm going to steal it. I just think that's a great expression.
Can I just make a comment?
Sure.
The tyranny of the fairing is really the challenge. What heavy lift gives you is the ability to take the mass out of the equation.
Right.
We often think that things cost what they weigh. Actually, heavy lift and a large fairing. The large fairing gives you the big aperture. And the things we want to study, the black holes, exoplanets, they're incredibly dim, and you need a large aperture to resolve them. So that drives the size. But if you have heavy lift and a large fairing, suddenly heavy things don't cost more. In fact, they cost less because it makes the engineering easier to get optics into space.
Right. You get folks like me off the program faster.
Okay, Rob, I have several questions for you that have come in from the audience. I'm just going to pick one. Does the Blue Moon architecture include a crewed capsule or habitat?
So Blue Moon is a demonstration mission to really focused on taking cargo to the surface, and we're working very closely with NASA on that. It's really focused on cargo to support any future human settlement missions. So.
Okay. And for Mike, For Mike, all of a sudden I was fine. Can you talk a little bit about how SLS's capabilities can help conduct science sort of by lingering
Sure.
in the neighborhood, if it were?
Sure. When you're effectively unconstrained in mass, when you talk about the size payloads we can get on an SLS for a destination, It facilitates much greater propellant margins, and that allows a planetary orbiter to make orbital plane changes, periapsis lowering maneuvers, attitude reorientations, and basically you can capture an orbit and loiter there for years effectively. So instead of flying by and taking pictures on your way out of the solar system, you can go there, loiter for months or years studying the planet, changing the view, getting different viewing angles and so forth. So that's quite a bit of an enabler, I think, in terms of enhancing science at the destination.
That's a use of it I hadn't really thought about before, this panel. Okay, just got another question here, which is one of my favorite questions, so I'll just throw it out to anybody in the panelists. In the space community, we argue that humans are hardwired to explore. The individual who's sending the email says, curious about the perspective of panelists as to what motivates us to do so.
Well, I'll jump in on that, and I'm sure everybody else has an opinion, but I really actually do believe we are genetically programmed to want to explore. I think that's why we have, evolved to be the dominant species. It's not just opposable thumbs. It's the fact that we bring, reasoning and curiosity to the table. Think about, babies. We're born, and I have a bias, we're born as scientists. We're trying to figure out how does the world work? And we're learning the laws of physics as we play. We're also learning, what's good to eat, what's not good to eat, a side issue. And that's biology, so that's okay too. But we're born as scientists. We're trying to learn how the world works. And that carries into all of our activities. We heard, a talk yesterday about, is space at lunch, is space normal? Are we going to bring all of our activities to space? And yes, humans, as we leave planet Earth, are going to bring all of our activities to space. But most important is that curiosity, the need to know. The need to know is, part of exploring. All of science is exploration. Going to planets to live, well, if you're going to do exploration, you want to live. I think, the interesting dynamic are folks who get into the discussion about humans versus robots. Yeah. And I think if you look at what's going on planet Earth and pick a topic, self-driving cars, we have a world where robotics is part of our lives now. That discussion is essentially over. We're always going to be doing it in partnership. That said, the robots don't discover anything. It's still people, and probably always will be.
Okay, anyone else?
Yeah, our species, ever since the beginning, since the first person walked out of that valley, actually at least two,
yeah, at least two.
Since the rest of us are here, did that several million years ago. We've continued that trend. We all grew up on stories of the greatest scientists, the greatest business people, the greatest adventurers, the greatest engineers, and it's what we're all built to do, whether it's a business, whether it's going into space, repairing a telescope, whether it's building the next one, or large rockets. I think it's very fundamental to our nature, and it's intensely human.
Actually, we can do a quick demonstration. Blue has an interest in millions of people in space, and we have bright lights, but I'm just going to ask for a show of hands, and this is, a captive audience, but how many of you would like to go to space? So what's interesting is that not everyone raised their hands. Right. Mm-hmm. And so I think there's probably some, genetic variation of people who have a stronger desire to take risks, to explore than others. And I think that's characteristic of human behavior on planet Earth.
Down here?
John said something, he used the word curiosity, and I think we as humans are curious, and that is a very important part of who we are. And are there people, is there life outside of the, planet Earth? And I say, why not? So, I believe there is, and we have to continue to look, and it may be beyond this, small region of space that we happen to reside in, and so we need to develop the systems and technologies to get there, and the heavy lift is so crucial and critical to get in there. The scientists, the autonomy folks, the people building robots, the launch vehicle developers, and the space systems developers, we all have to work together to get to that eventual vision. So, yeah.
Mike, any thoughts?
No, I think it's well said by everyone.
And the genetic variation piece, which I think is very interesting, I just have a professional interest in it. If you stop and think about it for a while, any species that stays in a very small area is essentially a sitting duck. It's a sitting duck with regard to natural catastrophe, it's a sitting duck with regard to famine, sitting duck with regard to plague. And so if you look at the history of species on this rock, they tend to migrate. And it's not all species that do that, but among those species that do that, by the same token, the entire population does not migrate. So you have elements of the migration of the population that do go out there and migrate while everybody else sort of stays here and makes babies and does whatever else they're doing, okay? Then this population goes out here. Some of those people, some of those critters survive and some of them don't. But to keep going out there and establish a new place. And what that does is actually supports the survival of the species because you're located in more than one area. And so it kind of makes sense that from a genetic point of view, you would evolve some genetic combination that would maybe lead some members of the population to move, to want to get up and move, to take the risk, as you say. So it's kind of an interesting perspective. Okay, is there anybody in the audience that wants to raise their hand and get a question in? And we've got about a minute left. No? We've answered everything you wanted to know about heavy lift and science. Apparently. Okay, you guys are really good. Well, I want to thank our panelists.
Well, since we have a couple of minutes, let me ask the next question, because I agree with Rob that the fact that we're all here, the fact that we're at the Broadmoor in Colorado Springs talking about space, and we're all involved in the space industry is incredible. Life on planet Earth, that's the only example we know.
Yeah.
I find it compelling that there must be life elsewhere. It's a question of how common.
Right.
And the cool thing is, it is a scientifically answerable question with the technology we have, with the capabilities we're developing. But it's interesting when I talk to public groups, not everybody agrees with that. So how many people think that it's compelling that there must be life elsewhere in the universe, which is vast? How many people think that in the next 20 years, we will discover existence of at least microbial life somewhere in the universe? So that's a pretty good number. To do that, we need to continue to develop the science experiments, the engineering, the lift vehicles, and we need to continue to explore. Otherwise, we won't have that answer in the next 20 years, or maybe 30 years. So,
and we will need everything we've got to do it. So
it's a hard
keep on
problem.
Working. Yeah. Thank you again. Thank you to John, Jonathan, Rob, and Mike. Really appreciate you being here. And thanks to all of you for listening so intently and thinking about all this and moving us forward.